Right, okay, special relativity. As I said, it is a little bit difficult to get your head around first of all, but just bear in mind that there are basically two equations in this that you need to know and you need to be able to put numbers into to get your marks. Obviously, ideally, we'd like you to understand it as well, but don't panic too much if you're thinking, whoa, okay, everybody thinks that in this first time round. Okay, so those are the two equations. You saw them on that video that I made you watch on Friday. Time dilation and length contraction. So that's how you work out how the time differs depending on whether you're traveling very, very quickly or stationary. And same with how the length differs. Okay. So what is special relativity? Okay, so it's all down to Einstein and talking about how light moves, and how matter moves because of light. And I showed you a video a couple of lessons back about the Michelson-Morley experiment. And he said that he did this experiment where he shone light, and they thought at the time that light went through something called an ether, like a material called ether, just like sound travels through air, light travels through ether. And they said that if light travelled along with the same direction as ether, it probably would travel faster than if it travelled in an opposite direction or at right angles to the ether. But he proved that that wasn't true. Okay, so he proved that light travelled the same speed no matter what. Okay. So something that's really important when we talk about special relativity is these frames of reference. Okay. So frames of reference is just like if you're on a train, you're technically moving very, very fast on the train, but to you feel like you're stationary. Okay. But if somebody was observing from outside the train, they would see you whizzing past on the train, so you'd be moving very quickly. Okay, so similar kind of thing. This example here is we've got an old school train here, and this is moving at a constant speed of 60 miles per hour. So you get it from your seat and you go to buffet car, which is located towards the front of the train. So you're going forwards on the train. So you're walking at a speed of 2 miles per hour along the train corridor. Okay, so to you think you're just moving at 2 miles an hour. Okay, you're just moving forward 2 miles an hour. Okay, because that's how you perceive it. That's your frame of reference. So your speed relative to the train. So if you look down at the floor, the speed that you are traveling at is 2 miles per hour. Okay, so relative to the train, you're just moving at 2 miles an hour. You're moving 2 miles an hour faster than the train, really. If you carried on walking at 2 miles an hour, you'd end up walking off the edge of the front of the train, wouldn't you? Your speed relative to the ground, however, is if you could look through the train and see the ground whizzing past, what do we think it's going to be? 62, yeah. So you're traveling at the speed of the train plus that 2 miles per hour. So do you see what I mean? Like, you're still traveling at the same speed, but depending on what you're referring to, your reference frame, you're traveling at a different speed. Right, your speed relative to a cyclist traveling anti-parallel to the train at 10 miles per hour. So basically that means you've got a cyclist and he's traveling anti-parallel, so that means the opposite direction to the train, at 10 miles per hour. So your speed relative to a cyclist traveling anti-parallel to the train, now we usually get two answers for this one. What do you think it is? Ah, okay, this is interesting. This usually happens. Okay, so hands up if you think it's 52. Or people have changed their minds. Hands up if you think it's 72. Oh, it's kind of 50-50. It is 72, because if you think about it, if something goes past the opposite direction, it seems like it's whooshing even faster. Yeah, so it is 72. If you were traveling by the train, so if the train was going like that, and you were like, it would feel like the train was going slightly slower than it actually is if you were traveling in the same direction. But because it's traveling in the opposite direction, it's whooshing past you faster. Yes. Yeah. See. Sorry. because you're basically moving in that direction, it's moving in that direction. So you're basically adding up the distance traveled. So the train's going in that direction, you're going in that direction, okay? So if you were just stationary, the train would be going at 60 miles every hour, okay? But because you're going in that direction, you're moving some miles per hour that direction, and the train's moving some miles per hour in that direction. So the amount of miles per hour that's different is bigger. Does that make sense? Sorry? If they're moving together, well, the cyclist is kind of keeping up a little bit with it. So if you were standing still, it would be going at 60 miles per hour. But because the cyclist is kind of keeping up with it, it seems like it's going slower than it actually is. Okay. I did tell you it is quite difficult to get your head around. Okay, so it's kind of like, I think it's something you've got to keep thinking about, and it is really tricky. I remember the first time I did this, I was like, no, I don't know. No, I don't agree with that. But that's how it works, okay? So have a think about it. If you're ever on a train or if you're on a bus and something goes past you, okay, does it look like it's going faster or slower, depending on which direction it's going in? Okay. Right, and great. Things become more complicated when you consider the ground outside is not at rest. It's rotating very quickly around the centre of the Earth's moving very quickly around the sun moving very quickly around the galaxy, which is also moving around space, okay? So we tend to, in physics, we just sort of say, oh, the ground's our reference frame usually, okay? But, so this example highlights a subtle but important problem in physics. In order to fully define how an object is moving, it has to be given a frame of reference. So we usually just give it a frame of reference. And up until now, we've just been saying, oh, it's normally just the ground. Okay, the ground is still. We're assuming it is. So the laws of motion worked out by Galileo and Newton, which is what we've used so far, depended on the assumption that absolute motion exists, i.e. motion with reference to something at rest. However, everything we know of in the universe is in motion. So, can we find absolute rest against which to measure absolute motion? Don't know. I mean, there might be something, the very sort of centre of everything, but we don't really know. So, next page we talked about already, so that Nicholson-Morley experiment. So we can skip past that. And then we'll look at special relativity. So, Einstein was the guy that put all this in motion. So Einstein he did a lot of thought experiments. He thought a lot. Okay. So he had two postulates, and these are really important when we talk about special relativity. Okay. And two, I guess, definitions. These aren't your postulates. Postulates are bold ones here. That's just definitions, sort of scientific definitions. So paradigm is a typical example of pattern of something, a pattern or model, and a paradigm shift is a fundamental change in that. So basically, Einstein brought about this paradigm shift. Okay, so a lot of work have been done developing theories of this luminiferous ether, and it took someone from outside of the established order to see things a different way and see a way forward with the problem of light. Okay. So Einstein's theory is very simple. So it all boils down to these two postulates. The laws of physics must be the same for all observers, no matter their frame of reference or their reference frame. So that's one. So laws of physics don't change. And the second thing that doesn't change is the speed of light. It's constant for all observers, no matter their frame of reference. And it's because that speed of light is constant that other things have to change. Okay, so we talked about that time dilation, the length contraction. Something has to give. Because we know the laws of physics don't change. So distance is speed times time. Doesn't matter where you are. But if the speed stays the same, then the distance and time tend to have to change to fit in with that, the law, the postulate. So the first of these two postulates is easily agreed upon. If it was not true, We would need to apply different laws of nature to different systems based solely on what they were doing at the time. For example, to calculate the speed of someone, you measure the distance and the time taken to cover that distance and divide the first by second. You would not need to do anything different if the person walks on a moving train or if they walk past the station platform. The same method is used and the same relationship applied, though observers may disagree about an absolute speed of the person if they switch from one frame of reference to the other. But you still use distance is speed times time. That equation still is true. The second, the speed of light is constant, is this paradigm shift, okay? So we're just saying that it does not change on how you view the universe and everything in it. There's a huge wealth of experimental evidence that this is true. However, many physicists were initially unwilling to make the break from their disproved theories. Right, so the consequences are the important things here. The consequences of laws of physics are the same, speed of light is the same no matter where you are and no matter how fast you're traveling. So everything in Einstein's theory of special relativity is simply a logical consequence of these two basic postulates. At high speeds, non-intuitive relativistic effects, so weird things, are observed and things get a bit weird. So what Einstein discovered is that in order for all observers to measure the same speed for the beam of light, time flows differently and space sometimes contracts. So this is where it does get quite strange. Okay, so I've got quite a nice video to show you to prove what I mean about this. So it's using the same theory that we're going to go through in a second. But basically, one of these thought experiments was, imagine like a clock, okay? But this clock, instead of like a tick-tock metronome or something like that, what it is it's a beam of light that goes up and down. One, like up, down, up, down, up, down. Okay? So let me show you the video because I think because the distance changed, then the time would have to change to compensate for it, because we know that distance is speed times time. Okay? Now, it's not really noticeable at all until you get very, very quick. The speed of the thing that's moving becomes very, very quick, like almost near to the speed of light. But it does happen. Okay? So even that, there will be a minute difference in time. Okay? Right, so we're going to go through sort of the physics behind that in a little bit more detail. There's a bit of a proof, sort of mathematical proof involved in this that you don't need to know, but it's interesting where it comes from. Okay, so we're going to go through it, but I'll tell you when you can you don't need to panic about it. Okay. Right, so we've got that clock, okay, made out of two mirrors and some light, and it's going up and down. Okay, so the distance that light is traveling is basically, we're going to call the distance between the mirrors d. Oops, if I change my pen back. So that distance is d. Okay, so the distance that light is traveling is d plus d, so it's 2d. Okay, so the time taken to return to the bottom of the mirror, to go up and down, is, well, time is distance, is distance divided by speed. So the distance is 2d, and the speed is the speed of light. Okay, because we're looking at the speed of light here. Okay, so the time taken to return to the bottom of the mirror is given by t, we'll call it capital T to distinguish between it, is 2d divided by c, so distance divided by time. So I'm going to just label that equation 1, because we'll probably come back to that later. Okay, so now we're looking at this situation that we saw from the audience point of view. Hi, Becca. Let us suppose that this clock is now moving past us with a speed v. We would see something like this. So instead of we see it going up and down, we saw it in that video, it's going side to side. Okay, so that AB is bigger than D. Okay, so the person holding the clock and moving with it, they would still see the first scenario. So if you were holding it, just pretend you were on that moving seat, you'd just see this in front of you. You wouldn't see it going like that. Okay, and the rest of you pretend you're, and then then pretend you're watching somebody doing this on the moving seat. You see them do this, they like do that. Okay. The person holding the clock and moving with it would see the first scenario. The person watching it move past would observe the second picture, and the light beam would have travelled further before returning to the bottom mirror. However, this observer still measures the speed of light to be the same as that measured by the first observer. To keep the speed the same, they must measure a longer time interval. So time increases. So, right, I'm going to redraw that diagram up here just so I can see what I'm referring to. Okay, so that's A, that's B, that's C, that's our distance D. So I'm going to call that AB and that BC. Okay, so length AB and BC are equal. So those are the distances that it's travelled from the people that are observing it. The time measured by the stationary observer from this clock is, therefore, we call it T dash. Remember, time is distance divided by speed. So that divided by speed plus that divided by speed. Okay? So that's where it says AB over the speed of light plus BC over the speed of light. And because we know AB and BC are equal, we can just say that the time measured by the person sitting in the audience, in that example, is 2 times AB divided by the speed of light. Remember, that's just again, time is distance divided by speed. Okay, so it says there, yeah. So following on from this, the rest of this page you don't need to know. You'll never need to recreate it, but it is quite interesting where it comes from. Okay, so the distance between A and C will depend on the speed at which the clock is moving, or the speed at which that chair was moving. Okay, so we call that a V. And the ratio of the lengths AB to AD, so if we call that D, will be equal to the ratio of the speeds C and V. So let me just redraw that again. So AB, BC, that's D. So that's AD. Okay, so basically that's the speed of the mirror and that's the speed of light. So because the speed of light is travelling along AB and the speed of the chair, the trolley is moving along AD, then we can say that they're equal to the ratios of the lengths of the triangle are equal to the ratios of the speeds. So AB over AD is equal to C over V. And if you rearrange that, you get AD equals V over C times by AB. Okay. So we're going to label that, oh, sorry, I wanted to label this one first of all, 2. And we'll label that 3. Okay. We're also dealing with a right angled triangle. So we can say that AB squared equals AD squared plus BD squared. Okay. And if we replace AD by what we worked out in this number 3, B over C times AB, then we get AB squared equals V over C times AB squared plus BD squared, which is just our distance, lowercase d. And then that rearranges to give an expression for AB in terms of V, C, and D. So if you rearrange that, you end up with AB equals lowercase d, so that's the distance between two mirrors, divided by the square root of 1 minus the speed of the thing that's moving, so in that case the chair, divided by the speed of light squared. Which one? This one? That one, it's just a rearrangement of the equation. I'll do it later for you if you want. Right. But all you need to know is just, it's the same equation, it's just rearranged, but I'll do it later. So the time from the person moving relative to the clock can be expressed as, now remember equation 2, t dash was 2ab over c. So we've got ab there, so 2 times that over c is 2 times that divided by c. So 2d over c times by that whole thing in the square root. And then recall that the time measured by the person holding the clock is 2d over c, so that was equation 1. So we've got a 2d and a c here. So we can replace that with just t without a dash. So we've got t dash equals t over square root of 1 minus v over c squared. And that is the equation that you need. So if you lost me partway through that, don't worry about it. I'll let you reread it as well. But that equation is what you will be using. Okay? Where? Yep. Yeah? Yeah. So, oh, right, okay, so this is it. So, basically, guys, the question, so we said that this direction is the speed of the chair, and this direction is the speed of the light. That's where the light goes. So we can say that the ratio of these two lengths is the same as the ratio of those two speeds. So AB over AB is C over A. Yes. Okay, so just to write down, sorry? Yeah. Just to write down everything in that equation, what it means. Listen. So V is the speed of the moving clock or the moving thing. T, without the dash, is the time measured in the frame of reference of the moving clock. So T is the traveller's time. Okay, the person that's travelling or the thing that's travelling, time measured by them. I'll write that down in a second as well. C is the speed of light, and T dash is the time measured by the person that the clock is moving relative to, so the stationary observer. And this effect is called time dilation. So let's just write that down somewhere. So T dash is the observer's time. So they're stationary. T is the traveller's time. That's E, isn't it? And V is the speed of the traveller. I'm sure I don't need to write down what speed is. Just the way it's written. There's no real reason for it. I suppose it just does so you don't get mixed up with any other time. Did you get what, sorry? Yes. Yeah. Okay. So, just to finish this off, there's a thing called the Lorentz factor. Okay. So, if looking at that equation again, T dash equals T over square root of 1 minus V squared over C squared. So this is sometimes, it says often, I'd say it's sometimes written as T dash equals T times by sort of gamma. Okay, so where that gamma is known as the Lorentz factor. Okay, so the Lorentz factor is all of that stuff here. Okay, so Lorentz factor is 1 over square root of 1 minus V squared over C squared. Okay. So sometimes in the question you might be given the Lorentz factor, which makes life a lot easier for you, because all it is T dash equals T times by that Lorentz factor. let's go through this worked example. A rocket is traveling at a constant 2.7 times 10 to the 8 meters per second compared to an observer on Earth. The pilot measures the journey as taking 240 minutes. How long did the journey take when measured from Earth? Not always, not necessarily. Okay, right. Because if you look at it, you can rearrange that. It could be a ratio. You could have t dash over t. Yeah. Okay. So t is the time for the person that's moving. So 240 minutes. The speed is 2.7 times 10 to the 8 meters per second. Speed of light is 3 times 10 to the 8. And we want to know what the journey, how long the journey would take from the stationary observer, so t dash. So all you do, and as Nicola was asking, do you need to change it into seconds? You can do if you want to, but if you look at it, actually it's a ratio t dash over t would be equal to 1 over 1 minus blah, blah, blah. So it's technically a ratio, so the differences would cancel out. But if in doubt, just change it to seconds if you want to. You put all those numbers in. You need to be careful with your square rooting and your squaring and things like that. And you come out with a time measured from the stationary observer as 550 minutes. So an observer on Earth would measure the journey as taking 550 minutes, i.e. 550 minutes would have passed from the stationary observer's point of view, whereas 240 minutes would have passed from the pilot's point of view. Okay, so time has travelled differently. And just something that might make life a bit easier for you, you can rewrite v squared over c squared as v over c in brackets squared. Okay, so that sometimes can make the calculation simpler, particularly if the speed is given in the form of a fraction of the speed of light. So the speed in the above example could have been written as 0.9 times or 9/10 the time the speed of light. So the calculation could then be written as 0.9 c divided by c is just 0.9. So it's 0.9 squared. Okay. So you could rewrite it like that. So 0.9 c over c squared, and c's would cancel out. Just might make life a bit easier for you. If you forget about it, don't worry. Just put all the numbers in. Right, okay. Have a go at example 1a. So a spacecraft moves at 2.7 million meters per second for 10 minutes according to its onboard clock, so according to the traveler's clock. How much time has passed for the stationary observer? Okay. So have a go at that. So your equation is t dash equals t over 1 minus v squared over c squared v is the speed of the traveler. So you're wanting to find t dash because you're wanting to find the stationary observer's time. Sorry. Guys, can you just turn the volume down a little bit? I can't hear the question. No, because the minutes will cancel each other out because it's a ratio, so it doesn't matter. In 10 minutes. So, yeah, 60 times, yeah. Yeah? Yeah, not nice. So you should be getting for 600 seconds. So pretty much no change at all because I kept mine in minutes. You don't need to, no, because yeah, if you want to just stick to changing in seconds, yes. Yeah. Yeah. Maybe. Oh. I wouldn't worry about it too much. We're going to go through it in a second, Nicholas. Okay, so. See the part that is T over T? Yeah. Is it the T on top over the T dash? Yeah. But it depends which way around you're going to rearrange it. But yeah, could be. Yeah, I think it depends on which way around you do it. But yeah, that's fine. 10.000. As long as it's 10.000 something, it's fine. Yeah. Oh, yeah. Right, so you can see that even though it's travelling at 2.7 million meters per second, there's still hardly any change, okay? So that's really quite slow compared to the speed of light, which is 3 times 10 to the 8, okay? So you have to be travelling very close to the speed of light for anything to really affect anything, okay? So, example 1b, this is horrible maths, by the way. At what speed, we'll go through it together, would an object need to be travelling for a minute to last an hour? Okay, so that means for a minute, in terms of the traveller, so the traveller t would be 1 minute, and t dash would be 60 minutes. So make sure they're the same unit. Okay, you can keep them in minutes or keep them in hours, but they both need to be the same. Okay. Obviously, c is the speed of light, 3 times 10 to the 8 meters per second, and we want to know what speed that was happening. Okay, so start off with our equation. T dash equals t over square root of 1 minus v squared over c squared. Okay, so t dash is 60, t is 1 minus v squared over c squared. I'm not going to put 3 times 10 to the 8 in yet because it's just more difficult to rearrange if you've got bigger things in. So I'm just going to keep it as c, but we know that c is 3 times 10 to the 8. Okay, now lots of different ways you could do this. What I would do, what I do is I don't like square roots, so I get rid of them as soon as I can. So what I would do is square everything, first of all. So I would end up with 60 squared equals 1 over 1 minus v squared over c squared. That's what I would do. You might do it a different way, that's absolutely fine. Just to reiterate, you won't be asked to rearrange it in this way. You'll either be asked to find t or t dash. So don't worry too much, it's not very nice maths. Right, then what I would do is I get that 1 minus v squared over c squared up. Okay, so I would go 1 minus v squared over c squared equals, I basically swapped the 60 squared and the 1 minus v squared over c squared. Okay. Then I would get my v squared and c squared alone as a subject. So I would say, because I want it to be positive, I'd say 1 minus 1 over 60 squared equals v squared over c squared. Then I would want the c squared away from my v squared, so I'd I would times everything by c squared. So c squared 1 minus 1 over 60 squared equals v squared. And then you just work it out because you know what c is 3 times 10 to the 8. So 3 times 10 to the 8 squared times by 1 minus 1 over 60 squared is v squared. So you end up with v being 299958330. So pretty much 3 times 10 to the 8. So very close to the speed of light. Yep.